Welcome back, kids. Charlie Abuso here, your chemistry teacher. This is the beginning of the notes for phases. We're going to go through number 23. Here we go. This is a cute little model diagram of the three phases of matter: solid, liquid, and gas. And what I'd like you to do is to fill in what are called 6 phase changes by name. What do we call it when a solid becomes a liquid or a liquid becomes a solid? You know these words, okay? The word for solid to liquid, of course, is melting. And when a liquid becomes a solid, that's called freezing. Now, what about liquid to gas or gas to liquid? When a liquid becomes a gas, that's one thing. And then the reverse, when a gas becomes a liquid. Now, we call liquid to gas vaporization. That includes both boiling, which happens at the boiling point, and it includes evaporation, which actually happens at every temperature. Really cold water will vaporize. It will evaporate. It evaporates much slower, but if you had a glass of water in your room and you forgot about it, it would evaporate. Vaporization includes boiling and evaporation. The reverse, though, when a liquid is formed from a gas, when a gas becomes a liquid, that's called condensation. Now, there are 2 more, and these are the ones that are always on the regions because they're the hard ones. You don't see them too often. When a solid jumps directly to the gas phase, or when a gas goes directly to the solid phase. Now, we don't see this very much. Excuse me, we did see, I'm having a little bit of seltzer, and as the warm body warms up the seltzer, the carbon dioxide that was in solution expands and turns into a bigger gas in my stomach, and I apologize. It's chemistry, though. We did see when iodine turned directly into a gas, and we also saw when iodine gas turned directly back into a solid. And those words, of course, are sublimation, when a solid goes to the gas phase. And you can think about this: when the gas deposits itself onto itself into a solid, it deposits into a solid. So you need to know these 6 phase changes. Keep them in your head. Make sure you just memorize them. And don't say boiling or evaporation. Make sure you use the V word, vaporization. Okay. Now, there are also, for water, 2 very important temperatures. Every substance has a melting point and a boiling point, right? Or reverse, the freezing point or the condensation point. But for water, you have to know them, right? Water is ubiquitous, and you are expected to remember these. Now, there are 3 phases of water: solid, liquid, and gas. And between solid and liquid is called either the melting point or the freezing point. And it depends. Is the solid warming up or is the liquid cooling down? The same temperature. There's one temperature, the phase change temperature between solid and liquid. Sometimes it's melting, sometimes it's freezing, sometimes it's both. If you hold the temperature exactly at 0 centigrade, exactly at 273 Kelvin, you will have both freezing and melting, and freezing and melting, and freezing and melting forever, both phases. At the liquid to gas phase change, which we call vaporization, but in this case, because it's happening at a specific temperature, the boiling point, this is the boiling point temperature, okay? It's also the condensation temperature. At 100 degrees centigrade, liquid water can jump into the gas phase, but gas, H2O, steam, can also condense. And if you hold the temperature at exactly 100 centigrade, you can get both of these phase changes at the same time. Now, the temperature between solid and liquid, 273 Kelvin, or 0 centigrade, that's also called standard temperature. Both of these only occur at what's called standard pressure. Now, we haven't talked much about pressure yet, but we're going to start talking about it tomorrow. Pressure is the impact that gas has on everything, and gas bangs on everything. And if you had a pot of water on the stove, the gas would be banging down on the surface of the water, and the water would have to overcome that downward bombardment of particles. It'd have to boil. It would have to overcome its internal attraction and the bombardment from above. Pressure, if you change the pressure, lower pressure or higher pressure, that would actually change these temperatures. These temperatures, STP stands for standard temperature and pressure. At standard pressure, normal pressure, water will freeze or melt at 0 centigrade. And at standard pressure, water will condense or boil at 373 or 100 centigrade. Okay, this is it. But if you change the pressure, you can get hotter or lower boiling points, or you can get colder or warmer freezing and melting points. Now, we're going to be looking at graphs. I talked about this in one of the intro videos. Something called the heating curve. The heating curve shows what happens to a substance, phases, as you add heat. Temperature changes, phases change. If it's a heating curve, the temperatures are going up, right? Because you're adding energy, and it shows the phase changes as heat is being added. On a cooling curve, which is the opposite, you start out really hot and you remove energy, and the temperatures are going to go down, or they're going to get flat during the phase changes. And it will show the energy associated with the phase changes and the phases as heat is removed. Now, to draw a heating curve or a cooling curve, this is red and blue here. The heating curve would require you to know the melting point and the boiling point. A cooling curve, which is the opposite, we're removing energy, you'd have to know the freezing point, the condensing point, right? Now, the temperatures are the same. The boiling point, oh, look, I spelled melting wrong. Look at that. Ooh, it's throwing my eyes off. The melting point is also the same as the freezing point, and the boiling point is the same as the condensing point. But you're either warming or cooling, so you only get one or the other. You don't really have a freezing and melting point at the same time, usually. Okay. Now, we're going to draw the heating curve for water. I showed this to you in the intro video. Most important, in black at the top, you can't start the graph at absolute zero. You cannot. There is no absolute zero. So we're going to pick a point slightly above zero. It's going to be 0, 0 in the corner. Time 0 on the bottom axis, and temperature 0 Kelvin. We can't start at 0 Kelvin. So we put in the two most important temperatures for the heating curve for water, which of course would be the melting point and the boiling point. You know these numbers in Kelvin, 273, 373. Now we're going to start the graph just above 0 Kelvin, point A. Now at point A, we're going to add heat at a constant rate. Now the temperature at point A, I don't know exactly what it is. There's no real scale. This could be very off. It's only this much is 100 degrees, and then this much might be all the way to 0. That might be 273. So this could be any really cold temperature. It's a little bit fuzzy there in the corner. But this is really cold ice. And as we add heat, on that red line going up from A to B, it's solid ice. It's still solid ice. As we add heat, it's warmer solid ice, but it's still solid ice. And it's going to stay solid ice all the way up to the melting point. So as we add heat, the temperature, of course, is increasing. And temperature is actually a measure of the kinetic energy, the motion of the particles. Now, these particles of H2O, they're molecules that are stuck together. They're solid ice. But at point A, they are vibrating slowly. And at point B, they are vibrating quite a bit. They're still stuck, but they're really buzzing, relatively speaking. Now, something special happens at point B. We reach what's called the melting point. And that is the warmest temperature that this solid can stay solid at. If we add even more heat, we can't make hotter ice. At that point, the ice starts to break apart and turn into a liquid. And what happens is, as we're adding heat, we don't get an increase in temperature anymore. And that's really kind of weird. We'll talk about that a little later. As we add heat from B to C, the temperature is not going up. All of the energy that's being added is used to break the ice apart into a liquid. And the temperature will not go up until all of the ice is turned into a liquid. The temperature remains constant. During a phase change, there is no increase in temperature. There's a change of phase. But at some point, at point C, all of the solid is gone and it's now all liquid. And once the substance, in this case it's water, once the substance is all liquid and we continue to add heat at a constant rate, the temperature will go up. And so at point C, when it's all liquid, as we add heat at a constant rate, the temperature goes up and up and up and up and up and up, and it goes all the way up till that other special temperature. And that special temperature for water called the boiling point is 373 Kelvin. At 373 Kelvin, liquid water cannot get hotter, not at standard pressure. At that point, if you add even a little bit more energy, you can't make it hotter anymore. That's as hot as liquid water can get. At D, if you add any more energy, you start to blow this liquid apart. It can't hold on. It's moving so fast, but it's barely holding on. A little more energy, and it literally explodes apart, and it turns into a gas. So as you add heat, once it's the hottest liquid it can be, and you add heat, it can't get hotter, it's going to go through a phase change. Look, it's flat again. During a phase change, there's no temperature change. So from D to E, we're adding energy, adding heat at a constant rate, but the temperature of the liquid water cannot get hotter. It's at the boiling point. That's the hottest temperature that a liquid could be. And for water, it's 373 Kelvin. And it continues to stay at a constant temperature because all the energy that we add goes to breaking this liquid apart into a gas. But finally, at some point, at point E, all of the liquid is now a gas. And any extra energy we add will, in fact, increase the temperature of the steam, not of the water liquid, but of the gas water, the steam. And so from E up to F. And now F has an arrow up there. How hot could it get? Well, in a lab, if you had a contained system with a Bunsen burner, you might be able to get the steam up to 300 or 400 centigrade, right? Maybe 500, 600 Kelvin. But you could take this water to the sun. The sun is 1,000,000 degrees. It can get really hot, right? That arrow means it's just going to get, the steam can get hotter and hotter and hotter. The particles will move faster and faster and faster. Okay? Not to infinity, but to infinity and beyond. No, I'm just kidding. It just can get as hot as you can make it. This is the standard issue heating curve. Now, this heating curve, like I told you in the last video, the intro video, this curve is the exact same heating curve literally for any substance in the universe. The only difference between this heating curve and the heating curve I told you for gold is, for instance, it says water in the title. You'd have to change that word water to gold. And those two temperatures, 273 and 373, well, gold doesn't melt at 273 or boil at 373. You have to look those temperatures up on table S. But if you change those two temperatures and you change the title, the gold heating curve looks exactly like this. Every heating curve looks exactly the same. Solids get warmer till they melt. Then the liquids get warmer till they vaporize. And then the gas can get as hot as you can make it. Every heating curve looks exactly like this. There's only three little changes: the title, and what is the boiling point, and what is the melting point. Now, this chart, it's tight here. I'm going to make it a little bigger in a minute so you can see it. We want to talk about what's happening on segment AB. What's happening to the temperature? What's happening to the kinetic energy? I want to talk to you about something called potential energy. And then I want to know what phase or phases is present from segment A to B. So segment A to B, let's just do this together. Segment A to B, the temperature is clearly going up. It starts out, we'll guess, 170 Kelvin. It goes up to 273. The temperature is clearly increasing. Temperature and kinetic energy are like a hand in a glove. Whatever the temperature does, the kinetic energy does. If the temperature goes up, the kinetic energy goes up. Actually, the kinetic energy goes up, so the temperature goes up. Adding heat makes the particles move faster, or in this case, makes them vibrate faster. The faster or more motion they have, the greater we measure the temperature. Now, potential energy, we haven't really talked about yet. I'm going to talk about this over time. I'm going to introduce it now. It's a little tricky to understand at our level of chem. In all honesty, there are units. We're not going to deal with them. We're just going to talk about the idea of potential energy. Potential energy is the energy of phase. And from A to B, it stays only in the solid phase. It's not changing. Solid is solid is solid. One energy can change at a time. And since the kinetic energy goes up and the phase stays the same, we say that the potential energy is constant. Okay, and we're going to leave it at that. We're not going to make it too fancy. There's more to it. It'll come up in the next couple of lines, and then over the next couple of weeks, we'll talk more about what is potential energy. There's a lot more to it, but not really too much more in our class. We're just going to coast a little. Now, what happens from B to C? Now, this is an important section of the graph. It's not so obvious, right? Because we're adding heat, but look, the temperature is constant. The temperature is 273 Kelvin. It stays 273 Kelvin. What happens from B to C? From B to C, the temperature is constant. And the temperature is constant because the kinetic energy is not changing. What's happening from B to C? Well, look at the phase. It's going from the solid phase to the liquid phase. All the energy that we're adding is changing it from solid to liquid. Now, liquid is a lot more excited. I don't know what the word would be, maybe, but solids are blah, and liquids are a little bit more mobile. The potential has gone up. The liquid has more potential energy, same temperature, same kinetic energy, right? The particles are humming along at B, and at C, they're loose, but they're not moving any faster. So the kinetic energy is constant, but now they're loose. So we say the potential energy has increased. Only one energy goes up at a time. And if the temperature is constant and the kinetic energy is constant, and we go from solid to liquid, then the potential energy goes up. From C to D, it's obvious the temperature goes up. It goes from 273 to 373. We warm the water up right through its whole liquid phase. The temperature goes up, the kinetic energy goes up, and if the kinetic energy goes up, what's the potential energy do? Well, it doesn't do anything. It started out as a liquid at C, it's still a liquid at D, it's the same phase, and at our level of chem, potential energy is the energy of phase, and it's liquid, doesn't change. And that makes sense because if the temperature and kinetic energy increase, only one energy at a time can change. D to E, no temperature change. Look, it's 373. This is the boiling point. There's one temperature. The temperature does not change. From D to E, the temperature stays steady at 373 Kelvin. So the temperature is constant. And if the temperature is constant, the kinetic energy and the temperature are pretty much the same thing. One's a measure of the other, really. If the temperature is constant, the kinetic energy is constant. But we've gone from liquid to gas, and gases are way more mobile than liquids. We say that gases have a higher potential energy than liquids. So the potential energy increased. If we're adding energy at a constant rate, energy must increase. We're adding it, right? Energy has to be accounted for. But if the kinetic energy is steady, we almost have to invent a new energy to explain this, and that's where potential energy comes in. The energy of phase. Gases have a higher energy associated with it than a liquid does. So gases are higher than liquids, liquids are higher than solids, potentially. Now, from D to E, it starts out at 373 and it gets as hot as you can make it. The temperature goes up, the kinetic energy goes up, but the gas phase is always in the gas phase. It doesn't change. So the potential energy is always the same. This chart, Wegman-Seltz, it's the best. This chart, it's obvious, but you need to commit it to memory. One energy goes up at a time. Temperature and kinetic energy do the same thing. In a heating curve, the temperature is going up or it's steady. There's no going down, right? We're adding energy. Everything's either increasing or the temperature stays steady and the potential increases. If you add energy, things get hotter or the potential energy goes up during the phase change. There's no decrease of anything. We're adding energy. Things got to get more energetic. Now, look at these cool pictures. Look at the bottom left, these slow moving dots. These molecules, this diagram representing molecules moving slow. And on the right, we have what are called hotter molecules. Look at those molecules really bouncing around much faster. Temperature-wise, slow-moving particles are colder, they have less energy, and the faster-moving particles are going to be hotter. Now think about this. You put your hand in the kitchen sink and the water's cold and it's coming out. The molecules that are coming out, the water molecules are stuck together and they're not moving that fast because the temperature's cold. So when it gets on your skin, your body temperature is probably hotter than the water. So the water will warm up to body temperature. Heat will exit your body and warm up that water. But if you run your hand under really, really hot water in the kitchen, the particles are moving super duper fast. When that water hits your skin, the molecules of water are so fastly moving, it's going to transfer that energy into your skin, and it's going to make the molecules in your skin move that fast, and it's going to kill some of your cells. It's going to hurt. You're going to get burned. So heat can transfer, right? So if it's cold water on your skin, your body heat transfers out. You get a little cool, right? Because the heat goes out, the cold water makes you feel cold. The water doesn't make you feel cold. The loss of heat from your body makes you feel cold. But if really hot water touches your skin, that energy transfers into your cells, and that shakes up the molecules in the cells to the point sometimes that they break apart. And if enough of them break apart, you can see the injury to your hand. And we call that getting burned. But it's really just the destruction of cells, in this case due to excessive heat. Now, temperature is deemed when the particles are moving faster. Faster particles means hotter. Colder temperatures indicate that the particles are moving slower, right? Kinetic energy. The energy of motion is called kinetic energy. The higher the kinetic energy, the hotter things are. The lower the kinetic energy, the cooler things are. Now, whatever the temperature does, the kinetic energy does too. Temperature goes up, kinetic energy goes up. Temperature goes down, kinetic energy goes down. If the temperature increases, the kinetic energy increases too. If the temperature decreases, the kinetic energy decreases too. And what if the temperature stays steady? What does the kinetic energy do? At a steady temperature, kinetic energy stays steady too. Hand in glove. Kinetic energy and temperature are in a sense doing the same thing all the time. In a sense, they are the same thing, just a different way to understand it. Now, during a phase change, like on segment BC or DE, heat is being added at a constant rate, but the temperature and kinetic energy stay steady. This is called the law of conservation of energy. You need to memorize this. Energy cannot be created or destroyed in a chemical reaction or a physical change, but it can be transferred. Right? We had the law of conservation of matter or mass. This is the law of conservation of energy. We have to be able to account for the energy, whether it's a chemical reaction or if it's a phase change. We have to account for it. And energy cannot be created, destroyed in a chemical reaction or a physical change, but it can be transferred. How do we explain that when we add heat, the kinetic energy remains steady on these two flat parts of the graph? Well, we have to talk about that other kind of energy. Heat energy is added, so energy must increase. If the kinetic energy won't increase because the temperature stays steady, then it's the potential energy that will increase. Potential energy in our class, potential energy is called the energy of phase. Solids have the lowest potential energy, liquids have medium, and gases have the highest potential energy. To make a solid into a liquid, you have to add energy. To make a liquid into a gas, you have to add energy. And once you've given it that energy, it now possesses that energy. The particles are moving faster. But when you change phases, if H2O is at the freezing point at 0 degrees centigrade, and you add energy, now it becomes liquid, but it's still at 0 degrees centigrade, you've added energy, but the kinetic energy is constant. You've changed the phase, you've changed the potential energy. The higher energy is liquid than solid and gas than liquid. Which has the most potential energy? Gases have the most potential energy. Which phase has the least potential energy? Solids have the least potential energy. During a phase change from solid to liquid, melting, energy is added, but the temperature stays at 273. What energy increases during the phase change? Potential energy, not kinetic. Temperature is the same. The ice has a what kind of potential energy? The liquid has a what kind of potential energy? The ice has a lower potential energy. Liquid has a higher potential energy. Lastly here, 23. Can both kinetic and potential energy change at the same time? Absolutely not. One energy at a time. All right. This was quick. Phases is cool. Phase class number 1. Read the basics. Let's try an experiment. You guys are going to do everything I tell you to do, and we're going to see how much smarter you are in 3 weeks when phases is over compared to maybe normal, right? When you don't do what I ask. Do what I say this time. Read the basics. Over and out, kids. Thanks for playing.